Let's solve the cascading tank problem for the height of the water in tank 1 and in tank 2. And we're going to do it in 4 different ways. First way, using Euler forward time stepping. Second way, using Euler backwards time stepping scheme. Third way, using the trapezoid rule time stepping. And the fourth way, the analytical solution. So let's write down what the equations are. So it's the time rate of change of the system, the state of the system, which consists of 2 variables, the height, h1, and h2 in each tank. And that's equal to a matrix that multiplies the state, h1 and h2, plus the non-homogeneous term, which is the source term, r of t divided by the cross-sectional area of tank 1 and 0 in tank 2. In this one, we had 3 time constants. If you remember, there was minus 1 over tau 1, minus 1 over tau 2, and then there was over here a 1 over tau 3. And to keep everything as simple as possible, I'm going to assume that 1 over tau 3 is the same as 1 over tau 2. So I'm going to do that to keep everything as simple as possible. So that's a special case. And to this, I add the initial condition, h vector is equal to h1 at t naught is equal to h2 at t naught. And these are just 2 numbers which I organize in a vector, which I'll call h naught. Now it's useful to define, give these things some names. So I'm going to define the matrix here, this matrix, I'll call that M. So M is going to be minus 1 over tau 1, 1 over tau 2, 0, minus 1 over tau 2. And then H will just be what's already defined, but it'll be in general. This is at t naught. H of t will be h1 and h2. And the source function will be defined as r of t divided by a1 and 0. And with these definitions, my governing equation becomes simply d by dt of h is equal to m times h plus s, subject to the initial condition h at t naught is equal to h naught. And now we're going to do the 3 time stepping schemes. Over here will be the Euler forward, over here the Euler backwards, and the last one will be the trapezoid rule. So for all these 3, we want to discretize dH dt, and we will always do it the same way. dH dt is going to be approximated by h at time step n plus 1 minus h at time step n divided by delta t. And that will be common to all 3 methods. The difference is that when we do the Euler forward, we're going to evaluate the right-hand side, the time tendency term, at time step n. Whereas in the Euler backwards, we'll evaluate this at time step n plus 1. And in the trapezoid rule, we're going to take the average of these 2. So let's write down what this all means. We have h at n plus 1 minus h at n divided by delta t is equal to m times h at time step n plus s at time step n. For this one, h at time step n plus 1 minus h at n divided by delta t is m at time step n plus 1 plus s at time step n plus 1. And finally the trapezoid rule, h at time step n plus 1 minus h at time step n divided by delta t is equal to the average of these two. So that will be m times h at n plus h at n plus 1 divided by 2 plus s at 1 plus at n plus s at n plus 1 divided by 2. And now I'm going to, in each case, I will isolate h of n plus 1 on one side and the other terms on the right hand side. So for the first scheme, h at n plus 1 is equal to h at n plus delta t times m times h at n plus delta t times s at n. And now all these quantities are known at time step n, and I can move forward to time step n plus 1. In this case, it's a bit more complicated. I get h at n plus 1, and I'll also have a delta t times m times h at n plus 1. So minus delta t times m times h at time step n plus 1 is equal to h at n plus delta t times s at n plus 1. And this one here, I can factor out the h at n plus 1, so I get the identity matrix minus delta t times m times h at n plus 1 is h at n plus delta t times s at n plus 1. Now this is a 2 by 2 matrix. 2 by 2 matrix. And this is a 2 by 1 vector, right? And the state has two unknowns. So this corresponds to two equations and two unknown. So the Euler backward scheme involves solving a linear system of equations at every time step. So we say that this is an implicit scheme in that it implicitly defines what h is in terms of a system of linear equations. Whereas this one, the Euler forward, was much more straightforward because we did not have to solve any system. We could just evaluate the right hand side here, and this gave us the left hand side directly. So this one is an implicit scheme. This one is known as an explicit scheme. The trapezoid rule is going to give us a different implicit scheme. So here, if I collect all the terms, I will have the identity minus delta t over 2 times m times h at n plus 1 is equal to the identity plus delta t over 2 times m times h at n plus delta t over 2 s at n plus s at n plus 1. So this one, all these quantities here on the right hand side of the equal are all known at time step n. Right? This one is evaluated at time step n plus 1, the source term, but the source is a known function. And here we have only h at times n. This one is the unknown, and again, it's defined in terms of an implicit system where we have to solve two equations and two unknown. This is again a matrix, a 2 by 2 matrix. And this is again is the state 2 by 1 vector. So we have two equations and two unknowns to solve. At every time step, we have to solve this linear system. So if I define some quantities here, this one I don't need to do anything. This one I want to define a matrix for this. So I'll define this one to be B, to be I minus delta t times m. And over here, I'll define this matrix here to be A I minus delta t over 2 m. Actually, I'll define this one to be, this one will be a with a plus, and b will be this one. And I do that because these look more the same. The only difference here is that my time step is a half of what it is. Otherwise, it's more or less the same matrix. I minus delta t over 2 times m. And then I can use these to show what the time stepping will be. I'll take a few time steps on paper, and then we can go to MATLAB. So a few time steps of the Euler forward. Oh, actually I should define a matrix over here, right? This one, I'll call this A, because here I could factor out the H. So let me define I plus delta t times m, which is consistent. I have the plus and the plus. So this A and B are very similar to these ones. Forward. Starting from the initial condition, h1 is h naught, h2 is a times h1, which is known because that's just h naught, plus delta t times s1. h3 is a squared h1 plus delta t a s1 plus delta t s2. And we can keep going like this forever. h4 is a cubed h1 plus delta t a squared s1 delta t a s2 plus delta t s3, and so on. For the Euler backward, starting from h naught, h1 is equal to h naught, and then I have b times h2 is equal to h1 plus delta t times s2. So that if I want to solve for this, I'll get b inverse h1 plus delta t b inverse s2. That will be h2. Then h3 will be b times h3 is h2 plus delta t times s3, which is equal to h3 is equal to b inverse h1 plus delta t s3, and then I could substitute what I had for the previous for h1. Oh, sorry, this should have been h2 here. Hold on, that was h2. So h2 is known from here. Substitute in, I get b inverse of b inverse of h1 plus delta t b inverse of s2 plus delta t. I need this inside the bracket, delta t s3. So the Euler backwards seems to you get repeated application of the inverse B matrix, whereas over here you get repeated application of the A matrix. And then let's do the trapezoid rule. So now we get, starting from H0, then to get H1 we have B, H2 is equal to A, H1 plus, where are we? This is A, and this is plus delta T over 2 S1 plus S2, and then H2 therefore will be equal to B inverse of A, H1 plus delta T over 2 S1 plus S2. Oh, we can't see. So this is this scheme. So this matrix here is the B matrix. B times H2 is equal to this matrix A times H1 plus delta T over 2 times the average. And then if I solve, I bring the B inverse over here. And let's do one more time step. H3 is going to be B inverse of A times H2 plus delta T over 2 S2 plus S3. And if we want, we can substitute back in what H2 was. So for the trapezoid rule, the expressions get kind of messy. The code, though, is going to be there'll be hardly no difference between the trapezoid and the Euler backward scheme. Both of these will involve solving a linear system, so there'll be the effect of taking the inverse of the matrix B will have to be done at every time step. In fact, what we're going to do is we're just going to use what MATLAB calls backslash, which solves the system without explicitly computing the inverse of the matrix. So let's go to the computer and solve it. So I need to pick some parameters for this system, and we're going to pick time scales. So tau 1, I'm going to choose tau 1 to be a fairly fast time scale, so 1 second. And tau 2, I'll pick this one long to be 10 seconds, so 10 times longer. And I'll also need to specify a forcing, R, and I'm going to pick that to be R of t over A. I'm going to make this a time-dependent function, which is sinusoidal, so I'll pick it to be, let's say, 0.01 plus 0.001 sine. And here I need to pick a frequency, and I'll pick that to be 2 pi divided by a period, and I'll pick it to be somewhere in between these two. So let's pick it to be 2 seconds. Let's pick it to be 5 seconds. 5 seconds times t. So this quantity here, omega, I'm going to define it to be 2 pi over 5 seconds. So somewhere in between those two time scales. And the relative size of these time scales is going to become relevant in which of these schemes or mostly which of these schemes, either the Euler forward, which is an explicit scheme, versus these two schemes, how well they do. These ones are implicit scheme in that you have to solve the linear system at every time step. Okay, so let's go to the computer, define my variables. Tau 1 is 1 second. Tau 2 is 10 seconds. Omega is 2 star pi divided by 5 seconds. Omega is frequency, is inverse second, 1 per second. And then I can define my source function, S, is a function of time, and it is a vector with 0.01 plus 0.001 times sine omega times t. Yep, that would be the source function, and then the direct source into the second tank was just 0. So all the flow came into the top tank. And then my matrix M is minus 1 over tau 1, 0. Oops. Tau 2 minus 1 over tau 2. That's the matrix M. I need to specify some initial conditions and a place to store the solution. So let's pick the time range I'm going to run. So suppose I'm going to run this for n is equal to 500 time steps. Number of time steps. And then the time I'm going to run this will be lens space between t naught, which I'm going to pick to be 0, to the end of this run. I need to decide how long I want to run it. Let's see. Let's run it for 500 seconds. Divided by n. So then dt is going to be the difference between time 2 and time 1. And then I can define for the Euler forward scheme. So over here, Euler forward, A is equal to I, which is the identity, the 2 by 2 identity, plus dt times m. I need a place to store the answer, right? I said that, but I didn't do it. So h is zeros 2 by n. All right, so h is going to be, each column of h will correspond to the state at a particular time. So the different columns are at different times. The first row will be the height in the upper box. The second row will be the height of the water in the lower box, in box 2. And then I'm going to be ready to start time stepping this. So my initial condition, if I don't change it right now, it will be 0 in each box. Let me reset it just so we can have something to look at. So 0.01, sorry, h colon 1 at the first time step. This is the initial condition. Will be 0.01 and 0.01 also. Let's pick it a little bit different, 2. All right, so this is at time t naught, or at time 0. The height in the first box is 1 centimeter, and in the second box is 2 centimeters. And then we're ready to time step. So 4k is equal to 2. I already know the solution at time step 1. That's the initial condition. To get time step 2 up to n, I will do the following. h colon, that's time step k, is, for the Euler forward, I have the scheme over here. It's just a times h plus delta t times s. So a times h at time step k minus 1, the value of the state of the previous time step, plus dt times s. And s I'm going to evaluate at time step e of k minus 1, previous time step. And then I say t at time, oh, t is already defined, end. That takes care of the Euler forward. So let me give these different names. So this is good, and I call this E Euler forward, E Euler forward, Euler forward, Euler forward. Now we're going to solve it again by using the Euler backward. It's going to be almost the same. Euler backwards. Now for the Euler backwards, this now becomes a minus, and to stick with my notation, this is what I'm calling B. This is Euler backwards, and this becomes B backslash H Euler backwards at time step k minus 1 plus delta t s n. Here, this will be at time step k, right? This is at n plus 1. So the same as on this side, n plus 1. Those are the same, and these are the same. I have k and k, whereas the one here is at k minus 1. And since I have to solve this system, I have the b backslash, which means solve the linear system b times this is equal to what's in between the round parentheses out here. And that takes care of the Euler backwards. And then finally, trapezoid rule. Trapezoid. Okay, and here I have to define A and B. A is I2 plus dt slash star m slash 2. B is minus slash 2. A with a plus, B with a minus, and they're both divided by 2. And then the solution will be B backslash, but here, the only difference is here I multiply by A. So this should have been A times trapezoid at k minus 1 plus delta t divided by 2 times the sum of s at time t k plus 1 plus s at time t at k. So did I get this all right? Let's see. Hold on. Too many parentheses. S at t at k. Close the first parenthesis plus s, close the second, like that. So the trapezoid is a matrix. B has to be solved, inverted. So I do the backslash. You could think of the backslash dividing through by B. But of course it's a it has to be divided from the left because they're matrices and they don't commute. The order of multiplication is not the same. And then on the inside I have this A over here multiplying this term, which is at times n, which is 1 less than on this side. So k minus 1 here, k on this side. And then for s I do the average. I have k plus 1. That was wrong, right? This down here should have been k and k minus 1. Right, here I have time step n and n plus 1 corresponding to n plus 1 on this side. So what I'm calling k here is the same as n plus 1. So that means on this side I have k and k minus 1. Alright, clear all. Example 2. Okay, they all check out. Let's make the plots. Figure 1. So this is the trapezoid rule down here. This is the Euler forward, the Euler backward. Now, one thing I can see, but maybe is hard to see from the video. First of all, they all look roughly similar. They both have an oscillation eventually as time goes on. the oscillation is much bigger on the upper box than the lower box, so transferring the water from the top box to the second box tends to damp out the oscillation in the second box. The water level at the kind of periodic equilibrium is around 0.01 meters for all three cases, but then the amplitude of this one appears bigger than this one, which in turn seems to be smaller than this one. So let's do a few things. First of all, so that the scale is always around here, I'm going to start off with both tanks being close to 0.01. So where's my initial conditions? Here. Let's pick them both close to 0.01. And this one. Second thing is maybe we don't need to run so long to see what's going on. So instead of doing 500 steps, I'm going to do only, I want the time to go up to 200. So instead of going up to 500, let's go to 200 only. That should be plenty. So I'll just run it out to here. Now the time step is going to be smaller, so it should be better resolved, because we notice here that the periodicity is not that well resolved. It looks kind of like clunky. All right, let's clear the figure, run it again. Okay, now maybe we can see better what's going on. So for the Euler forward, let me make the font sizes bigger too. Axis minus, no, not minus, axis 0 to 200, and then this I should give it an actual time t, and where's my lens space? So let's call this t equals to 200, t is 200, length of the simulation. And then I'm going to use that t to set my axis. T, and then the x and y axis, I'm going to start at 0.0095 all the way to 0.011. All right. So what can we see? The amplitude for the trapezoid rule appears to be a little bit less than the amplitude for the Euler forward. Notice how down here, or at least the lower ends are lower. They don't reach all the way down to the bottom of the scale, whereas in this one they do. So these two, the lows in these two cases, match more closely, but this one appears to underestimate the amplitude a little bit of the oscillation compared to the trapezoid rule. On the upper side, this one also appears to underestimate. And this one seems to be somewhere in the middle. So there's a big, smaller, and midpoint kind of amplitude. Now, it turns out that the trapezoid rule is the most accurate of all the three. And so if I further reduce the time step, this one should converge more quickly to a stable answer that won't change as we decrease the time step. But let's try it. So the number of time step here was 500. Let's double it to be 1,000. And run the model again. CLF, example 2. And now we still see some difference in the size of the amplitude here for the height, but maybe a little bit less. Let's double again, or multiply by 10 again, 10,000 time step. So my dt is going to be even smaller. Example 2. Now hopefully they've stopped changing. Yeah, so now they're starting to look, it's very hard, at least by eye, to see the difference between the three solutions. The amplitudes, here's a slight overshoot on the first one in all three cases, and then the amplitude is more or less the same. Let's run it for even longer, a shorter time, just 100 time steps. CLF, example 2. right? So they seem to converge. But now what we want to see is what's the behavior as we make the time step bigger. So there's very often when we run climate models, for example, this tension between wanting to have an accurate answer, which would push us to take very small time step, but then the need to save computer resources to take as big of a time step as possible so that we have to do fewer calculations. So notice here my time step dt is 1/100th of a second. We would like to be able to take bigger time step and still resolve what's going on. So we want to take the biggest possible time step so that we do fewer time step to do the same duration of simulation. And let's see what happens to these three schemes as we make the number of time steps progressively progressively less. Bigger time steps, less of them. So, and this time I won't clear the figure, so I'll just leave them so they plot one on top of the other so we can see the difference. If I divide by 10 and I run again, you can see where the difference. See that there's a much bigger difference between these two than the last one. Here I multiply this time step size by 10 and you can barely see the difference. They fall one on top of the other. But for the first two you start to see some differences, especially at the low end here. If I zoom out, you can see they don't quite match. And that's true of both the Euler forward and the Euler backwards. Let's do it one more time. All right, now they all have errors, but again, these two seem to get a bigger error than the trapezoid rule. And one more time. Maybe that's too brutal. Just 10 time step, that's not enough. Let's I had 100, let's do 50. Let's go more slowly here. Example 2. And now something crazy has happened over here. This one, it seems to be going right off the graph, right? I don't know if I can grab the hand to show you what happens to the solution. You have these giant peaks where things shoot off, especially here at the far end. Right, it's all the way up to 0.034, this one. So the Euler forward scheme, right, shoots off and becomes unstable, whereas the Euler backwards may not be very accurate, but it's still stable. So you can see the last one is this jaggedy curve that doesn't quite do a very good job at resolving the periodicity, but at least it's stable. And so is the trapezoid rule. These two are going to be stable, whereas the Euler forward is not stable. So the trade-off is that the implicit schemes are always stable, which is a good thing. You can take bigger time step. You do lose accuracy, but at least you don't blow up. The downside is you have to do a lot more calculations, because at every time step you have to solve a linear system. For this particular example, that wasn't a big deal because we're just solving a small 2x2 system. But if we were doing a climate model with millions of variables, doing an implicit time scheme becomes infeasible, because we would have to solve 1,000,000 equations and 1,000,000 unknowns at every single time step. So doing this once maybe is okay, but if you do it at every time step, then it's very expensive. So there's going to be other schemes other than these three that I've demonstrated that always try to push us as close to the edge of stability with bigger and bigger time steps. I should say the edge of instability. You want to run your code where the scheme is stable, but take the maximum possible time step. And different schemes will achieve that to different degrees. So let me see if I can zoom back up. Yeah. So if I took out the axis, maybe it'd be easier to see. So let me get rid of this axis thing here on this one. I'll just comment it out. CLF. And so you can see the amplitude seems to be growing with time. And if I ran it even longer, it would get even worse. So instead of going only 100, let's go for 1,000 time steps. Sorry, 1,000 seconds. Oh, but if I go longer, I need to increase the number of time steps so that this time step size will be the same. And you can see the Euler forward, there's this oscillation and it grows exponentially, which is not correct. This one doesn't grow, but it has this kind of spurious, weird oscillation that doesn't exist in the real solution. This one has it too, but to a lesser degree. Let's take more time steps to see if that goes away. And now it seems to be going away a little bit better. Alright, so that is what I want to show you about numerical schemes for linear systems. So all this worked out because my differential equations were linear. If they're nonlinear, then you have to do the implicit schemes are much harder to implement, because not only do you have to solve a linear system, or a system, sorry, not only do you have to solve a system, but it is a nonlinear system that you have to solve at every time step, which means it's not just enough to inverting a matrix. You have to iterate to approach the solution of the nonlinear algebraic system of equations. In the next video, we're going to solve the system analytically.